Let's take a look at some number patterns. Now, number patterns is actually a pretty broad topic, and in fact, if you look at the Common Core state standards, you'll see that even as far back as first grade, patterning is mentioned as being something that's very important when it comes to algebraic thinking. Here's an example of a problem from a 6th grade model curriculum unit from MODESE, the Missouri Department of Elementary and Secondary Education. It involves students looking at a pattern and trying to determine how they can continue the pattern and how to describe the pattern as being either linear or nonlinear. Now we're actually going to take a closer look at this problem and see if we can answer the question that's being asked. We want to create a table to show how many ties will be needed for each of the first 6 phases. So we're going to use some of the problem-solving strategies we've already talked about, one of which is to make a table, and then within that table we're going to see if we can find some patterns. So for example, if we look at the first phase, that means the square, it takes 4 ties to make the first phase. Now the second phase takes a total of 7 ties. Now if you look very carefully, you'll see that the second phase actually starts with the square from the first phase and adds 3 more ties onto that. The third phase is a total of 10 ties, and if you look carefully you'll see that the third phase is actually the second phase with 3 more ties. And in fact, that pattern can be seen in the table. If you look at how to get from 4 ties to 7 ties, you would add 3, and from 7 to 10 you would also add 3. So we can continue the pattern and see that for phase 4 we could add 3 more ties to 10 to get 13. For phase 5 we could add 3 more to 13 to get 16, and for phase 6 we could add 3 more to 16 to get 19. So that would be the first part of this question. Show how many ties will be needed for the first 6 phases. Now the second part is to explain how you know whether this pattern represents a linear or a nonlinear function. Now we'll be talking a little bit more about linear and nonlinear relationships later on in this course. But for now, if you take a look at how the phases and the ties are changing, what you'll notice is that the phases are increasing by a constant value of 1, and the ties are increasing by a constant value of 3. And because of that, this is a linear function. If the phases increase at a constant rate and the ties increase at a constant rate, then we would have a linear relationship. Now we're going to take a little closer look at the numbers that we've developed in this table and introduce a little bit of terminology as well. So we could consider the numbers that we see as representing a sequence, because a sequence is a pattern of numbers or symbols. In fact, we're going to look at the numbers in the ties column and look at that sequence of numbers. Each of the individual numbers in that sequence is called a term. So 4 is a term in the sequence and 13 is a term in the sequence. And in fact, because these terms have a particular pattern, meaning the pattern that we add the same amount every time, we consider this to be an arithmetic sequence, because in an arithmetic sequence we add a common number, which is called the common difference, to find the next term in the sequence. So in this particular sequence we're adding 3 to a previous term to get the next term, and that number that we're adding over and over again to get from one term to the next is called the common difference, which in this case is 3, and the letter that we use to signify a common difference is D. So for this sequence, D is equal to 3. Now you'll recall that we also had a certain sequence in these numbers. The first term was 4, and the second term was 7, and so on. we can signify the position of a particular term in a sequence with notation that uses a subscript to show the position of that term. So for example, in this sequence, a sub 1 means the first term in the sequence. So a sub 1 is equal to 4. And a sub 2, which would be the second term in the sequence, is the 7, and so on. Now each of these terms has a value. So if we think of a term as having a value, then we can think of the pattern that we're seeing in those values. So for example, the first term is 4. So we're starting with these 4 ties in the pattern. And then to get to the second term in the sequence, a sub 2, we notice that we added 3. So we could say that the pattern is we start with the 4 and then we add a single 3 to that 4. Now if we look at the next term, a sub 3, we would add another 3 to the second term, a sub 2. But if we look at how we get to that third term from the first term, we could say that we start with the 4 and then we add a 3 and we add another 3, which means we start with the 4 and we add 2 3s. To get to the fourth term, a sub 4, we would have to add another 3 to the third term, but if we want to describe how to get to that fourth term from the first term, we could say we start with the 4 and then we add 3 more 3s. To get to the fifth term, we add another 3 to the fourth term, or we could say we start with the 4 and then we add 4 more 3s. And to get to that sixth term, we could add a 3 to the fifth term, or we could also describe it as saying we start with the 4 and we add 5 more 3s to land on that sixth term. Now it's important to notice a pattern in terms of what number we start with and how we can get to a term in the sequence, because that will help us write an nth term formula for the sequence. So for this particular sequence, we could say we start with the 4, and then to get to a term in the sequence, an nth term, some term in position n, we have to add a number of 3s, and the number of 3s we would have to add is 1 less than the position that we're trying to reach. So for example, if you look at the sixth number in this sequence, a sub 6, to get there, we started at the 4 and we had to add 5 more 3s. Now that's a specific nth term formula for this particular sequence, 4 plus n minus 1 times 3. If we take a look at that, we could generalize it and say that for this particular sequence, we know that we always start with the 4 and then we add a number of 3s. So how could we get to the 100th term in the sequence? Well, we could start with the 4 and then we could add 99 more 3s, which would mean the 100th term of the sequence is 301. So for this sequence, think about the fact that the first term was 4. And think about the fact that the common difference was 3. So how can we take what we noticed about this particular sequence and write something that can be used to describe any arithmetic sequence? Well, if we do that, we have something called an nth term formula for any arithmetic sequence, which would be to find a number in the sequence, a sub n. We have to start with the first term, a sub 1, and then we add to that a number of common differences that's 1 less, n minus 1, 1 less than the position that we want to find in that particular sequence, the value of the position. Now, how can we use that for any sequence? So let's take a look at this particular arithmetic sequence, 5, 9, 13, 17. Now we know it's an arithmetic sequence because if we look at the terms, we'll notice that to get from one term to the next, we're adding a number. So to get from 5 to 9, or 9 to 13, or 13 to 17, we're always adding 4, so the common difference is 4. If we want to find the next three terms, we simply have to keep adding 4. So 17 plus 4 is 21, 21 plus 4 is 25, and 25 plus 4 is 29. So we can easily find more terms in the sequence by simply adding 4 and adding 4 and adding 4. But how can we write a formula that describes any term in the sequence? That's an nth term formula. Well, in order to write an nth term formula, we need to know the first term and the common difference. And we know both of those things. The first term is 5, and the common difference is 4. So, to find an nth term formula, all we have to do is take the first term, which is 5, and add n minus 1 times 4. Now we can use a little bit of algebra here and clean this up. So we could distribute the 4 and then combine the like terms and come up with a slightly neater looking version of our nth term formula. And keep in mind you can check this too. So if you look at the sequence 5, 9, 13, 17, let's say for example you wanted to find the second term. Now we know that that's 9, but take this nth term formula and substitute a 2 for the n. 4 times 2 is 8, and 8 plus 1 is 9. So we've got a formula that will generate any term in the sequence if we know the position, that would be the n, the position of the term we're trying to find. So with that in mind, how could we find the 100th term of this sequence? Well, we want to use this formula and find a term that's in the 100th position, and meaning, in other words, when n is 100, what's the value of this particular sequence? So when n is 100, 4 times 100 plus 1 is 401. The 100th term is 401. Now what if instead of saying what's the 100th term, in other words, instead of saying what value is the number in a particular position, what if I give you a value and ask you what the position is? So what position in the sequence is the number 609? Well, remember, we've got this nth term formula we've come up with. A sub n is 4n plus 1. Think of a sub n as meaning a number. So if I want to find a number in this sequence, I need to take 4 times n, which is the position, plus 1. So a number in the sequence is actually something I know. I know the number 609. What I don't know is the position. That's the n. So 609, a number in the sequence, is 4 times n, its position, plus 1. Now if we solve this equation, subtract 1 from both sides, and then divide both sides by 4, we have n equals 152. So the number 609 is the 152nd number in this sequence of numbers. Here's another example of the sort of question that might be asked of a student about sequencing. This is a 3rd grade sample map item from DESE. If you take a look at the table, you'll see that students are trying to complete a table. This is about boat rides, and there's some patterning going on. So they're being asked to find a pattern for the number of students in the boat. And the twist on this is, the question is, if there are 26 students in a class, how many boats will be needed so that all students can ride in a boat? If you look at the number of students, they are all multiples of 3, and 26 is not a multiple of 3. So when students complete that table, what they find out is that they will need to have a boat that isn't completely filled. So it's a little bit of a twist on that problem, but still what they're looking for is patterning in the number of students and completing that pattern. Okay, let's look at different sort of sequence of numbers. 4, 12, 36, 108. Another infinite sequence because of those 3 dots behind the 108. We're looking for a pattern, and what we don't see here is an arithmetic sequence because there's no number that we can add to each number, no constant number I should say, that we can add to each number to get the next number. So 4 plus 8 is 12, but 12 plus 8 is not 36. So we can still look for a different pattern, and in this case it's a multiplication pattern. If we multiply each number times 3, we do find the next number in the sequence. And because we're multiplying in this case, this is called a geometric sequence. In a geometric sequence, you multiply by a constant, which is called the common ratio, to find the next term in the sequence. So in this particular sequence, since we're multiplying by a 3, that's the common ratio, and the abbreviation for common ratio is an R. So in this sequence, R is equal to 3. Now, knowing what the common ratio is also allows us to find more terms in a sequence. But we have to be a little bit careful about that because sometimes the pattern that you're seeing is not the same thing as the value for the common ratio. For example, if I ask you to find the common ratio for the sequence 128, 64, 32, 16, most people when they look at this sequence see a division pattern. They're seeing that to get from one number to the next you divide by 2. And that's certainly true. If I wanted to know the next number in the sequence, I would take 16 and divide it by 2. But for a common ratio, we're looking for a multiplier. We're asking ourselves, what do you multiply each number times to get the next number? So one way you can find that multiplier is to look at any 2 consecutive terms in the sequence. So let's say we look at the 32 and the 16. If you take of those 2 consecutive terms, take the second number and divide it by the first number. So if I take 16 and divide it by 32, I'm going to get 1/2. So the multiplier to get from one number to the next is 1/2. 32 times 1/2 is 16. So that's the common ratio here, 1/2. Even though you're seeing a division by 2, common ratio is always considered to be the multiplier you use to get from one number to the next number. So let's look at the 4, 12, 36, 108 that we started looking at. Let's make a table, kind of like we did with the arithmetic sequence, and see if we can figure out something that's going on with the pattern of the terms and their values. So the first term here is 4. The second term is 12. The third term is 36. The fourth term is 108. Now the pattern that we're noticing is that we start with a number, the 4, and then to get to the next number, we have to multiply by something. So 4 times 3 is 12. So in order to get to the 12, we take 4 and we multiply it times 3. Now to get to the 36, we have to multiply by another 3. But if you want to describe a pattern that tells us how to get to that 36 from the first number, we'd have to say we start with 4, we multiply by 3, and we multiply by another 3. In other words, we start with 4 and we multiply by 2 factors of 3. To get to the fourth term, we multiply by yet another 3. So how do we get to the fourth term? Well, we start with the 4 and then we multiply by 3 3's. Now if you look carefully, the number of 3's we're multiplying by is always 1 less than the position of that term. So if I want to write an nth term formula for this particular sequence, I would say I would start with the 4 and then I have to multiply by a number of 3's, and the number of 3's I multiply by is 1 less than the position of the term I'm trying to find. If I want to find the 100th term of this sequence, then I would still have to start with the 4 and I would multiply by 99 more 3's. Now that's a really big number. So we're not going to try to write that in any other way other than 4 times 3 to the 99th power. So we've got this nice pattern going with this specific sequence of numbers, which has a first term of 4 and a common ratio of 3. Let's see if we can write an nth term formula just in general for a geometric sequence. Well, an nth term formula in general for a geometric sequence would be that we have to start with the first number, so that's a sub 1, and multiply that times the common ratio raised to the n minus 1 power. So that's a general formula for any geometric sequence. If we have a particular geometric sequence, we can fill in some values for the a sub 1 and for the r to come up with an nth term formula for that specific sequence. So let's look at another sequence of numbers. We want to know the next 3 terms in this sequence. And if you look carefully, you'll see that it's not arithmetic because we're not adding the same number over and over to get from one number to the next in the sequence. And it's not geometric because we're not multiplying by the same number over and over. So the pattern is actually something a little more subtle than that. If you take a look at the first 2 terms, 1 and 3, if you add 1 and 3 together, you get 4, which is the next number after 1 and 3. And then if you look at 3 and 4 and add them together, 3 plus 4 is 7, which is the next number after the 3 and the 4. If you look at the 4 and the 7, well, 4 plus 7 is 11, which is the next number after the 4 and the 7. If you add 7 plus 11, 7 plus 11 is 18. That's the next number in the sequence. If you add 11 and 18, that's 29. Well, do you see what's going on? We're always taking 2 numbers and adding them together to get the next number in the sequence. And if that's what you see happening with your sequence, you have what's called a Fibonacci sequence. In a Fibonacci sequence, you always add 2 consecutive terms to find the next term. Now, while it's possible to write nth term formulas for Fibonacci sequences, they're kind of complex, so we're not actually going to be doing that. So let's take a look at these 3 types of sequences. We've looked at arithmetic and geometric and Fibonacci sequences. Let's say we start with the first 2 terms of a sequence being 1 and 5, and we want to find the next 2 terms of the sequence. Now, that information isn't really enough to tell us what the next 2 terms is. We need to know something a little more specific, like what kind of sequence is it? If it's an arithmetic sequence, then we know that to get from one number to the next, we always add the same thing. So to get from 1 to 5, we add 4. So to continue this sequence, we need to add 4 again. So 5 plus 4 is 9, and 9 plus 4 is 13. Now what if it's not an arithmetic sequence? What if it's geometric? Well, that means there's a multiplier. So to get from 1 to 5, we multiply by 5. We're going to continue that pattern. So 5 times 5 is 25, and 25 times 5 is 125. And if it's a Fibonacci sequence, then to get to the next term in a sequence, we add the previous 2 terms. So if we add 1 and 5, we get 6, and if we add 5 and 6, we get 11. Now we said that we can write nth term formulas for arithmetic and geometric sequences fairly simply. So let's see if we can do that for these 2, arithmetic and geometric sequences. Let's start with the arithmetic sequence. So to write an nth term formula, we need to know 2 things. We need to know the first term of the sequence, which is 1, and we need to know the common difference, which is 4. So in general, the nth term formula for an arithmetic sequence is start with the first term, a sub 1, plus add that common difference, d, a total of n minus 1 times. Now that is a general formula for any old any old arithmetic sequence. For this specific arithmetic sequence, we would say that the nth term formula is 1 for the first term plus n minus 1 times 4 since the common difference is 4. And if we do a little bit of algebra here, distribute the 4 and combine the like terms, we have an nth term formula for this arithmetic sequence. Now how about the geometric sequence? We want to write an nth term formula for that. So to find an nth term formula for a geometric sequence, we need to know the first term, which is 1, and we need to know the common ratio, which is 5. Now in general, for any geometric sequence, the nth term is found by taking the first term a sub 1 times the common ratio raised to the n minus 1 power. For this specific sequence, the first term's 1, the common ratio is 5, so 1 times 5 raised to the n minus 1 power. That's an nth term formula for this particular geometric sequence. So far we've just been looking at continuing patterns and writing equations for patterns. Let's talk about what happens when this pattern of numbers that we have doesn't go on forever and ever. And if that's what we have what's called a finite sequence. It's a sequence that has just a limited number of terms. If we have a finite sequence, that means that we can do things like count the number of terms in the sequence. And there's several ways to do that. One way would be to find a one-to-one correspondence with the counting numbers. So here's an example of finding that one-to-one correspondence. Let's say I wanted to find out how many terms are in the sequence, 4, 8, 12, and then the pattern continues until we get up to 40. Now if we can find a way to match these numbers up with the numbers 1, 2, 3, 4, and so on, then whatever matches up with 40 is telling us the position of 40. In other words, how many numbers are in the sequence. So if you look at each of these numbers, you may notice that they're all multiples of 4. So what if we take each of the terms and divide by 4? We're changing the numbers in the sequence, but the question is how many terms are there? So the number of terms we started with is the same as the number of terms we have now when we've divided each term by 4. And it's pretty clear to see that if we've got the numbers 1, 2, 3 up to 10, we must have 10 numbers. So the original sequence also has 10 numbers. So is that a method that's going to work all the time? Well, it can. Sometimes it's not quite as obvious how to make that one-to-one correspondence. So let's say we want to find the number of terms in the sequence 4, 9, 14, and so forth up to 59. Well, it's definitely an arithmetic sequence. So one thing we could do to find the number of terms in the sequence is to recognize what the first term is and what the common difference is, and if we can find those two things, then we can write an nth term formula for this sequence. So for this particular sequence, we know that the first term is 4, we know that the common difference is 5, and we know that 59, which is a number in the sequence which happens to be the last number, can take the place of a sub n, meaning a number in the sequence. So what we're trying to find is the position, the value of n, for a number in the sequence, which is the number 59. So if we solve this equation for the n, we see that n is 12, so there are 12 terms in this sequence. So this is another way that we can find the number of terms in a sequence. We can actually use that nth term formula to identify the value of n for a number in the sequence which happens to be the last term in the sequence. Now remember, we can use these nth term formulas. We can also use a one-to-one correspondence if we see one that's fairly easy to use. So let's take a look at that same sequence, 4, 9, 14, up through 59. So it's a little bit trickier to get a one-to-one correspondence going with this particular sequence, but if you take a look at the terms, we know that the common difference is 5. So since the common difference is 5 between the two terms, if I can make each of these terms in the sequence look more like a multiple of 5, then I'll be a little closer to finding that one-to-one correspondence. So I'm going to start by adding 1 to each of these terms. Now remember, that does change the terms in the sequence, but I'm really interested in how many numbers there are. I haven't changed the number of numbers. So now I've got 5, 10, 15, up to 60. What if I divide each of those numbers by 5? Then I get the numbers 1, 2, 3, up to 12. And it's pretty clear to see that there are 12 numbers in that sequence of numbers, so there have to be 12 numbers in the original sequence of numbers as well. Now this one's a little bit different. How many terms are in this sequence? Remember, if I can find a one-to-one correspondence, that would be one way. One-to-one correspondence with the counting numbers, that is. That would be one way to identify the number of terms in the sequence. And what I'm noticing is that the base numbers are the same. What's changing are the exponents. So what I'm going to do is try to make the exponents match up with the counting numbers. So I'm going to subtract 1 from each exponent. And if I do that, then what I'm seeing is the exponents are matching up with the counting numbers. And since the last exponent is 19, there must be 19 terms in this sequence. So that's a quick look at some different types of sequences and how to continue the sequences and find terms in the sequences and count the number of terms in the sequences. There's lots of different things you can explore with sequences, so enjoy the explorations.